I'm going to run through some problems on the review, most of the problems on the review, as quickly as I can here. This first one asks us to find the derivative. We have the product rule going on here. We also have the power rule going on here twice because we have x cubed and we have x plus 1 to the 1/2 power. So when I do the product rule, when I take the derivative, I'm going to start by taking the derivative of the first one, so 3x squared times the second, plus the derivative of the second one. Using the power rule, we have 1/2 times x plus 1 to the power of negative 1/2 when we subtract 1, times the first. So that is our product rule. And then we can simplify this. Typically, I would just stop at this step. But I want to show you on this problem, I'm going to take it real far and show you how you can simplify this further. The first thing we would look for is what they have in common factors. And both terms have an x squared. And terms are separated by plus or minus sign, so this has two terms. And this is the part that's a little bit trickier. We can pull out this guy. So when I pull that out, we get x squared, and I'm going to pull out an x plus 1 to the negative 1/2 power because they both have a base of x plus 1 to some power, and negative 1/2 is the lowest power that they both have in common. So now I'm going to write my new two terms with these pulled out of it. So when I divide this by x squared and x plus 1 to the negative 1/2 power, I end up with the 3. And x plus 1 to the first power. Because 1/2 minus negative 1/2 would be 1. So that's going to be to the first power. Then in our second term, when I divide this whole thing by x squared and x plus 1 to the negative 1/2 power, we have that 1/2 x. We have an x left over. And then that's it, because x plus 1 to the negative 1/2 divided by x plus 1 to the negative 1/2 is just 1. Then what we can do from here, I'm going to simplify what's in the parentheses over here. So we'd have a 3x plus 3 plus 1/2 x. 3x plus 3 plus 1/2 x. So 3x plus 1/2 x is 3.5 x. I'm going to write that as 7 over 2x plus 3. And then over out in front, we still have this x squared and x plus 1 to the negative 1/2 power. Now I'm going to distribute that. We're getting real messy here. So when I distribute, now I'm going to have, when I take this whole thing times 7 over 2x, I have 7x cubed on top and a 2 and an x plus 1 to the positive 1/2 power on bottom, or I'm going to write that as the square root of x plus 1. Moving it to the denominator because it has a negative exponent. So I'm going to move it to the denominator where it has a positive power of 1/2. Then I'm going to distribute it over here, and we just get, this is a little bit easier, 3x squared over the square root of x plus 1. It's pretty easy to get a common denominator here, so I'm going to do it by multiplying the numerator and denominator of the second term by 2 over 2. So I have 7x cubed in the numerator. I have 6x squared in my second set now. And then I have a common denominator of 2 and the square root of x plus 1. So that's how you can simplify it. That was a pretty messy one. I just wanted to show you how you could get a common factor out of these two terms and keep simplifying it further and further and further from there. Most of the time, they're not that complicated. Okay, second example. We have cosine to the 5th power of 4x, and I'm going to rewrite that so it's a little bit easier to see what's happening as cosine of 4x to the 5th power. It means the same thing. So I have to use the chain rule here a couple of times. First, because I have an exponent of 5, I have to use the power rule. My power rule, when I find the derivative, would be 5 times cosine of 4x. And now that's going to be to the 4th power. So first I use the power rule. Now I need to take the derivative of the inside. So the derivative of cosine of 4x is negative sine of 4x. And I still have another inside of 4x, and the derivative of 4x is 4. So I use the chain rule twice here. Then when I go to simplify this whole thing, I have a 5 I can multiply by this negative and by this 4, so negative 20. I've got cosine to the 4th power of 4x, and I have sine of 4x. And that would be our answer. Another one, this one's actually really similar to the one we just did. I'm going to rewrite it as sine of 2 theta to the 1/2 power. So I've got the chain rule a couple of times again. When I start, I'm going to take the power of the outside, so using the power rule. So 1/2 of sine of 2 theta to the negative 1/2. Then I'm going to take the derivative of the inside. The derivative of sine is cosine, so that's going to be cosine of 2 theta. And I still have another inside that I need to take the derivative of to get 2. So when I rewrite this final answer, I have 1/2 times 2 is just 1. I am going to have a cosine of 2 theta in the numerator and the square root of sine of 2 theta in the denominator. Or you could write that as sine of 2 theta to the 1/2 power. All right, we've got a couple of rules we have to use on this one. We've got the product rule because we have two functions that are being multiplied by each other, and we have power rules we're going to have to use. So on this one, I am going to take the derivative of the first times the second plus the first times the derivative of the second. And for the derivative of the second, so derivative, I'm just doing the derivative of 2x minus 5 squared. I'm using the power rule, 2 times 2x minus 5 to the 1st power. And then because that inside I can take the derivative of is 2, I need to multiply by 2. So I'm going to simplify this second set a little bit. I've got 2 times 2, 4x squared times 2x minus 5. And then over here I have 2x times 2x minus 5 squared. I'm actually going to go ahead and simplify this all the way. 2x minus 5 squared is 4x squared minus 20x plus 25. I'm going to distribute that out. 8x cubed minus 40x squared plus 50x. And then I'm going to distribute over here too to get 8x cubed minus 20x squared. And lastly, I can combine all my like terms to get this as my final answer. The most important part, though, is that first step. From there, it's just using basic simplifying steps. Next one, we want to find the second derivative. I really care more on this one that we can find the first derivative. So because we have x's and y's, we are going to have to use implicit differentiation on this one. So one term at a time. So when I start, we're going to do of both sides. So on the left side of the equal sign, the derivative of x squared is 2x. The derivative of xy, we have to use the power rule here. So I'll do x times the derivative of y plus y times the derivative of x. And the derivative of x is just 1. Now I need to take the derivative of y squared, which is 2y times y prime. That's the implicit differentiation. And the derivative of 3, which is just 0. All right. Now because we're looking for the first derivative, I'm going to group my first derivative. Anything with a first derivative piece on one side of the equal sign, and I'm going to move everything else to the other side of the equal sign. I'm going to factor out that y prime, and then I'm going to divide to get y prime by itself. So if we were looking for the first derivative, we would be done at this step. But it asks for the second derivative. That's what those little squares mean. So if I need to find the derivative of what we just found, we would have to use the quotient rule in this one. And it does get pretty messy. So definitely I'm not going to simplify it any further, but let's practice the quotient rule. So the second derivative, quotient rule is low times the derivative of the high. So the derivative of the numerator is -2 minus y prime. So that's low d high minus high d low, derivative of the denominator. So derivative of x is 1, derivative of 2y is 2y prime, over the square of what's below. And then we would take this another step further, and I'm not going to simplify it any more than this next step. And anywhere where there is a y prime, I'm going to substitute what we just found for y prime. And this one gets really, really, really messy. And so I'm not going to simplify any more than this. Here's our y prime again. So I'm going to substitute. And that would be our answer. Okay, we're going to find the second derivative again. This one isn't quite as messy. I don't want to use the quotient rule just for that plain old 2 in the denominator. So I'm going to think of this instead as 1/2 times cosecant of x. And the derivative of cosecant is cosecant times cotangent. So our first derivative would be 1/2 of cosecant times cotangent. But it didn't ask for the first derivative, it asked for the second derivative. So if I have to find the second derivative, now I have to use the product rule. So I'm going to do the first function times the derivative of the second. The derivative of cotangent, what is the derivative of cotangent? Looking up the derivative of cotangent, I actually found out that I had the derivative of cosecant wrong. So the derivative of cosecant is actually negative cosecant times cotangent. So my first one should have been negative. So when I take the second derivative, I have negative 1/2 cosecant of x times the derivative of cotangent, which is negative cosecant squared, plus, now I'm going to take the second function, which was cotangent, times the derivative of the first. The derivative of negative 1/2 cosecant would be negative 1/2 times negative, so positive 1/2, cosecant times cotangent. Oops, and that did not look very clear. So that negative 1/2 turned into a positive 1/2 when I multiplied by the negative, which is part of my derivative. This is pretty messy. We can go further. Let's see. Cosecant now to the 3rd power. Actually, that turns into a positive when I multiply that out. And then over here, we have 1/2 cotangent squared and cosecant. Both terms have a 1/2 and a cosecant. And we're taking out cosecant squared and cotangent squared. And that would be it. That's a little bit of a doozy. Okay, next one. ln of x squared minus 4x minus 7 to the 1/2. Okay, so one thing that is really, really helpful here is remembering your log properties. Log properties say that if you have something to a power, when we're dealing with logs, you can write that power in front instead. So I can actually take that 1/2 power and write it in front. So now I have 1/2 times ln of x squared minus 4x minus 7. And then this becomes a much easier problem. So I'm going to keep that 1/2 in front. And then all I have to do is take the derivative of ln of x squared minus 4x minus 7. And the rule for taking the derivative of ln, so ln of u, when you take the derivative of that, it is u prime over u. So we're going to take the derivative of this, which is 2x minus 4, over the x squared minus 4x minus 7. And then this can actually be simplified because in our numerator, we can factor out a 2 pretty easily. And that's going to cancel out with the 2 that we have in the denominator. And so our final answer would just be x minus 2 over x squared minus 4x minus 7. So this one, I wanted to show you, this doesn't show up on the test, but I did want to show you this one because we can use log properties again. So just for future reference, we can rewrite that whole function using log properties. This one actually requires all of the log properties to be used. So first we're starting off with the product. We have x times x minus 1 to the 3rd power. And product says we can separate those. We're expanding the log with addition. I'm going to run out of room if I keep doing it there. Let me rewrite down here. So I'm expanding this. So I'm going to have ln of x plus ln of x minus 1 to the 3rd power minus ln of x minus 2 to the 1/2 power. And like I mentioned before, whenever we have exponents, we can rewrite these with those exponents in front. So this is 3 and this is 1/2. So that's just using properties of logs that we learned in Algebra 2. Now we're going to take the derivative of these logs separately. And remember, the derivative for the natural log is u prime over u, the derivative over itself. So on the first one, the derivative of x is just 1, so we have 1 over x. In the second one, the derivative of x minus 1 is 1 again, but we're multiplying it by that 3, right, over the x minus 1. And then we have 1/2. The derivative of x minus 2 is just 1, and x minus 2. And I'm not going to simplify it from there, but we could by getting the common denominator. Next one, how do we find the derivative with e? Right, we know the derivative of e to the x is just e to the x, but the derivative of e to the u is e to the u times u prime. That's the chain rule. So in this case, we have e to the u, so we keep it, times the derivative of that exponent, u prime. The derivative of secant is secant times tangent. And I'm just going to leave the answer just like that. So this is, again, just using some more rules. Our rule is, when we are talking about exponential functions, if we have a base, we'll call it the base a to the u power. Our derivative is ln of a times a to the u times u prime. So in this case, our base is 3, and our u is 5x, which means our u prime is 5. So when we take the derivative, we'll have ln of 3 times 3 to the 5x times 5. All right, let's see. H of x is f of g of x, and we're looking for the derivative at 14. So first, let's find the derivative of h of x. So this is chain rule. Because it's a composite function, we take the derivative of the outside times the derivative of the inside. And we're doing this when x is 14. So I'm going to take f prime of g of 14 times g prime of 14. Or in other words, f prime, g of 14 is 2, so f prime of 2 times g prime of 14, I can go ahead and figure out what that is. That's 5. So f prime of 2, working our way out, is 12 times 5. Our answer would be 60. Okay, we've got lots of stuff going on here. We've got the product rule. 2 different functions, so product rule happening here. And we're going to have to use the power rule. No chain rule in this one, though. So let's see. Let's use the product rule. So we have the derivative of the first one is 4x cubed times the second plus the derivative of the second times the first. What's tricky about this one is finding an answer that matches those multiple choice options that you can see on your end. So let's simplify. Between my 2 terms, I can pull out a 1/2 x cubed and an x plus 1 to the negative 1/2. All right, and so when I do that, I'll show you what that looks like. When I divide this by 1/2 x cubed, x plus 1 to the negative 1/2 power, 4 divided by 1/2 is 8. X cubed divided by x cubed cancels out. And x plus 1 to the 1/2 divided by x plus 1 to the negative 1/2 is just x plus 1. 1/2 minus negative 1/2 is an exponent of 1. Now we're going to do the same thing over here. We're going to divide by all that. We're going to divide by 1/2 x cubed, x plus 1 to the negative 1/2. The 1/2s cancel. These cancel. And then x cubed cancels out 4 of those. So we just have an x left right there. So I have 9x plus 8 times this 1/2 x cubed times x plus 1 to the negative 1/2. Let's rewrite this now. We have, I do not need to distribute. Okay, we've got x cubed over 2 times the square root of x plus 1. So I'm just rewriting this right here, and then times 9x plus 8. So times 9x plus 8. So that 9x plus 8 is in the numerator also. So this is the option that you're looking for. All right, using the table. So this first one, we're going to have to use the chain rule. We have the derivative of the outside times the derivative of the inside, and we're doing everything at -1. I should be a little bit more careful with my notation, but that's okay. F of -1 is 0, so I'm going to find g prime of 0 times f prime of -1. G prime of 0 is 4. F prime of -1 is 2. 4 times 2 is 8. Second one, derivative of the outside times the derivative of the inside, and we're doing it all at -1 again. So g of -1 is what we're going to find first. G of -1 is -1. So f prime of -1 is 2. G prime of -1 is 1. 2 times 1 is 2. For the last one, take the derivative of the outside. So g prime of x plus f of x, that's the derivative of the outside, times the derivative of the inside. Well, the derivative of the inside, the derivative of x is 1, and the derivative of f of x is f prime of x. So that's what this one will look like. Derivative of the outside times the derivative of the inside. Everywhere we see an x, let's go ahead and plug in that 0. And then we're going to work our way from the inside out. So f of 0 is what I'm seeing to do first. F of 0 is -1. So I'm going to take the g prime of 0 plus -1, which is just 0 plus -1 is -1. So I'm going to take g prime of -1 times 1 plus f prime of 0. F prime of 0 is -2. 1 plus -2 is -1. So I'm going to take that answer I get and multiply that by -1. G prime of -1 is 1 times -1 is -1. All right, second derivative. So let's start by finding the first derivative. When we take the first derivative of tangent of 5x, let's start right there. The first derivative that we're going to have to use the chain rule on. So the derivative of tangent is secant squared. So secant squared of 5x, that's the derivative of the outside, times the derivative of the inside. Derivative of 5x is 5. Now we're going to have to take the derivative of x squared. That's the easier part. The derivative of x squared is just 2x. So our answer is secant squared of 5x times 5 plus 2x. Oh, no, I'm like, why is that not the answer? Okay, it's because we haven't found the second derivative. We only found the first derivative. Okay, so let me rewrite this real fast before we find the second derivative. We have 5 times secant squared of 5x plus 2x. Okay, so when we take the second derivative, so the derivative of what we just found, I'm going to rewrite this actually a second time. Hold on. Let's rewrite that as squared. There we go. So when I take the derivative of this, I have to use the power rule first because that secant is squared. So I'm going to use the power rule and take that squared and multiply it by the 5 to get 10. So now I'm going to have secant of 5x, and now that's just going to be to the first power. Now I need to take the derivative of the inside, so I have to find the derivative of secant again, and the derivative of secant is secant times tangent, so secant of 5x times tangent of 5x. And then because 5x has a derivative, we have to multiply again by the derivative of that, which is 5. And then don't forget, at the very end, we have to take the derivative of 2x. So we need a plus 2 on the end. I'm going to multiply some things out to simplify this. So I'm going to multiply the 10 by the 5 to get 50. I'm going to multiply this secant of 5x by this secant of 5x to get secant squared of 5x. I have a tangent of 5x, and then we have this plus 2. All right, finding the derivative again, starting off with the product rule. So I'm going to take the first times the derivative of the second plus the derivative of the first times the second. Now I'm going to take the derivative of negative x, which is negative 1. And then I'm going to take the derivative of y squared, which is 2y times y prime. I'm going to move all my y primes to one side, and anything without a y prime will be on the other side together. I'm going to factor out my y prime. And then I'm going to divide to isolate that y prime. And that's our answer. Okay, finding the derivative of this curve. So we're going to have to use implicit differentiation again. So we're going to have power rule, we get 4x. Power rule, we get 2y times y prime. Then we have to use the product rule. So I'm going to do first times the derivative of the second plus second times the derivative of the first. So we actually get negative 1 times y. And the derivative of 4 is 0. So just like before, I'm going to group the things with a y prime on one side. And everything else will get moved to the other. Isolate the y prime. There's our first derivative. Part 2 says write the equations of the tangent lines when x equals 1. So the key here are these plurals. Equations of tangent lines. And the reason why there are 2 is if we plug in 1 into the original equation to find our points, because we need to figure out our y values, we end up getting, let's see, y squared minus 1y plus 2 equals 4. Or if I make that equal to 0, since it's a quadratic, I can factor. And so I get 2 values for y. Y could be 2 or y could be negative 1. So there are 2 points where x equals 1. There's a point at 1, 2, and there's a point at 1, negative 1. So we're going to have 2 different equations. So let's do 1, 2 first. So first I need to figure out what the slope of my line is. I know the point, I need the slope. So into that derivative we found in part A, we're going to plug in the point 1, 2. So I will get 2 minus 4 over 4 minus 1. I get negative 2/3 as my slope. So my point is 1, 2. My slope is negative 2/3. I can plug that into point slope form. There's my first equation. My second equation, I'm going to plug in the point 1, negative 1 into that same derivative we got in part A. And when I do that, I get negative 1 minus 4 times 1 over 2 times negative 1 minus 1. So negative 5 over negative 3. So my slope is 5/3. My point is 1, negative 1. And so in point slope form, it looks like this. Okay, another one. This one, taking the derivative of both sides, I'm assuming is the first question. I did not actually do that. And that's actually what I'm going to do on this one. So let's take the derivative of both sides. So derivative of x squared is 2x. Derivative of xy, I'm going to do first times the derivative of the second plus derivative of the first times the second. Now I'm going to take the derivative of y squared and the derivative of 1. Group my y primes together. Move everything else to the other side. There's my first derivative. And I actually like part C on this one. It says find all the x values where the tangent line is horizontal. So if we want the x values where the tangent line is horizontal when the slope is 0. So we're going to be setting what we just found equal to 0. And so if I solve this, I get 0 equals negative 2x minus y, which means that y equals negative 2x. And if y equals negative 2x, I'm going to substitute that back into the original. So anywhere where there's a y, I'm going to put a negative 2x instead. So I have x squared minus 2x squared plus 4x squared equals 1. So that's 3x squared equals 1. X squared equals 1/3. So x is positive or negative square root of 1/3. Or I guess the square root of 1 is just 1. So 1 over the square root of 3. Or you could rationalize the denominator. But those are the x values where the tangent line was horizontal. Or in other words, where the derivative equals 0. All right, we are looking for the derivative of the inverse at 10. All right, so for the inverse, for f inverse, the y value is 10. So we want to know first, for the original function f, where is the y value 10? So if the x value is 10 for the inverse, where is the y value 10 for the function f? And it gives us that point. It tells us that the y value is 10 when x is 6. So the point 6, 10 is on f. The point 10, 6 is on the inverse of f. So it doesn't tell us anything about the derivative of the inverses, but it does tell us something about the derivatives at f. So f prime of 6 is negative 5. Its corresponding point on the inverse of f is 10, and inverses have reciprocal derivatives. So negative 1/5 would be our answer. All right. Here's another one. Similar, but very different. Our x value is negative 12 again for our inverse function, which means for our original function f, the y value is negative 12. So the first thing we're going to do is plug in the y value for 12 to figure out what our x value is for f. What is the x value that gives us negative 12? That's what we're looking for. So we're going to solve these types of problems. First, we need to make it equal 0. So let me go ahead and add that 12 over. And then actually, to make this even easier, we can multiply everything by 3. So we get x cubed plus 5x plus 42. And now we're looking for what x value we can plug in there. So if you remember your rules for Algebra 2, possible solutions would be the factors of 42 over the factors of 1. So we're looking at plus or minus 1, 2, 3, 6, 7, 14, 42. I probably missed one in there. 21. That's the one I missed. And you can use synthetic division or just plug in for x until you find the one that works. For this particular problem, the one that works is negative 3. If I plug in a negative 3, we get 0. So that means f of negative 3 is negative 12. All right, so what we're going to do, because we know what the function f is, we're going to find the derivative of f. So using our power rule, we get 1x squared plus 5/3. That's the derivative of f. So the derivative of f at negative 3 would be 9 plus 5/3, or 27/3 plus 5/3, 32/3. So that's the derivative of f at negative 3. Which means because this point corresponds to this point, the derivative of the inverse of f at negative 12 is the reciprocal of that. 3/32 would be our answer. All right, 21. I'm going to start by rewriting that f. So right now it's to the 1/2 power. We're going to have to use the chain rule if we're going to take the derivative of this. Let me make sure I know what this question says. F of 0 equals 3. G is the inverse. Okay. So we want to start by finding, because this y value matches that x value. These are corresponding points. So basically the derivative at 0 of the derivative of f at 0 is equal to the reciprocal of the derivative of g at 3. Or I guess g is the inverse, sorry. So the derivative of g at 3. So we're going to find the derivative of f. I'm going to use the power rule. Then I'm going to use the chain rule. So now I need to multiply that by the derivative of the inside. The derivative of the inside, the derivative of e to the x is e to the x. The derivative of 3x is 3, and the derivative of 8 is nothing. I don't really need to simplify this. Let me go ahead and simplify a little bit before I plug in the 0. So in the numerator, I have e to the x plus 3. In the denominator, I have a 2 in the denominator, and then I'm going to move this whole thing to the denominator too, since it has a negative exponent. And I'm looking for f prime of 0, remember? So now I'm going to plug in 0 everywhere where there's an x. So e to the 0 plus 3. Anything to the 0 power is 1. So that's just 1 plus 3. And in the denominator, I have 2 times the square root of e to the 0, which is 1, plus 3 times 0, which is 0, plus 8. So I have 2 times the square root of 1 plus 8. So 2 times 3 under 4. 4, 6, 2/3. 2/3. I'm getting tired. Okay, so the derivative of f at 0 is 2/3, which means the derivative of g at 3, because they were corresponding points, is going to be 3/2. Just take the reciprocal. Oh, I think we're getting close. All right, 22. Arc cosine. So our rule for arc cosine is u prime over the square root of 1 minus u squared. So let's define some things before we get started. U is 3x squared minus 1, which means u prime is 6x using the power rule, which means that u squared is 3x squared minus 1 squared. And I'm just going to leave it like that. So when I plug all that into what we know is the derivative of arc cosine, u prime is 6x over the square root of 1 minus u squared. And I'm leaving it like that. Actually, I forgot my negative. I wrote down the original one wrong. So derivative of arc cosine is negative u prime over the square root of 1 minus u squared. And the last one I'm going to do. Similar, let's talk about arctangent real fast. So arctangent, the derivative of arctangent is u prime over 1 plus u squared. So in this case, u is 5x, u prime is 5, u squared is 25x squared. So we'll use that when we need to. But we need to use the product rule here. So I'm going to do the derivative of the first times the second plus the first times the derivative of the second. And this is where we have to use this rule. So u prime over 1 plus u squared. And we can just leave our answer like that.